In this video, we're computing a definite integral of dx over 9 plus x squared. And the key to this problem is to realize that we're essentially looking at the form of the derivative of an inverse tangent. So just as a quick reminder, the derivative of an inverse tangent is 1 over 1 plus x squared. The issue, of course, is that we have a 9 down there in the denominator, so we need to get rid of that. And we're going to factor a 9 out of the denominator before we start doing anything else. So I get a 1/9 out in front of this integral, and it's the integral from 0 to 3 dx over a 1 plus x squared over 9. Well, we're still trying to get a 1 over 1 plus a variable thing squared, and so we want to re-express x squared over 9 as x over 3 all squared. Okay, now I have a 1 over 1 plus variable thing squared, so I know I'm going to get an inverse tangent out of this. But the chain rule is going to be involved, and so there's a formal and informal way of handling that. So if I see the 1 over 1 plus x over 3 squared sitting next to the derivative of the interior function x over 3, then it's simple to guess the chain rule backwards. That's our informal method. So what I'm going to do is multiply the exterior of this integral by a 3 and the interior by a 1 over 3 so that I get the derivative of the interior function. So now I have a 1 over 1 plus x over 3 squared sitting right next to the derivative of x over 3, and I can see the chain rule operating backwards. I'll cancel the 3's out in front of this integral and I get a 1/3, and then I have an inverse tangent of x over 3. Again, when I differentiate that inverse tangent of x over 3, I get 1 over 1 plus the argument squared, and then the chain rule says now you have to tack on a factor of the derivative of the argument, which is 1/3, and we get back to the original integrand. Now we evaluate across the limits of integration, 0 to 3. Plugging in the upper limit, I get the inverse tangent of 1, the angle whose tangent is 1, and that's pi over 4. And then in the lower limit, the angle whose tangent is 0, and that's 0. And so I get pi over 12. Now, if you wanted to be a little more formal about this and use an explicit u-substitution, we could break in at this step, and we could say let u be the interior function. So let u be x over 3. And that means du is 1/3 dx. And I can write the integral as a 1/9. And it's the integral as x goes from 0 to 3. And the denominator in my integral is now a 1 plus u squared. And I can explicitly sub out for dx by saying that dx is equal to 3 du. And then I can pull that 3 out in front of the integral and cancel a 3 in the denominator from that 1/9, giving me a 1/3 out in front. And I arrive at the integral of du over 1 plus u squared, which I recognize as the derivative of the inverse tangent of u. So I end up guessing my antiderivative here, inverse tangent of u. And I'm evaluating this across the x limits of integration, 0 to 3. And now you could either replace u with what it is in terms of x, or you could transform the limits of integration to u space. And in this case, I'll go ahead and just replace it with what it was in terms of x. I like to mix it up. And u is x over 3. And I'm evaluating as x goes from 0 to 3. And we've already done this once before, and it comes out to pi over 12. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.